Hello and welcome to Nikolai's genetics lessons, and this video going to be about law of probability, how to apply rule of probability to pedigree and find the probability for the progeny to have a specific condition. And here is a problem. The trait is autosomal recessive. The question is, what is the probability that the bottom two people, number 4 and 5, have a child with the trait? And as usual, I recommend you to pause video here, try to solve this problem on your own first, and when you would be ready, you can run video again, and you can compare your answer with my answer and explanation. Really, this problem can be solved under 30 seconds. Now, when you work on your own, this may take you much longer, but after my explanation, you would be able easily solve such problems within just a few seconds or at least under 1 minute. And I always recommend to try to solve problem on your own first, because when you apply an effort, even if you made a mistake, when you got an answer and when you see where you made a mistake, it would be much easier for you to remember how to solve this problem. And I can give you example when Arnold Schwarzenegger were performed in his first movie. He used his different name. He performed under Arnold Strong, but then he switched to his original name, Arnold Schwarzenegger, and his producers insisted for him to use easy name, Arnold Strong, but he said easy to remember, easy to forget. So when you apply an effort, this of course takes some energy from your side, but later you would find that you would memorize solution much better. So how we are going to solve this problem? First of all, let's start analyzing this pedigree from people in the first generation, number 1 and 2, and we are already told that this is autosomal recessive genetic disorder, and it is very clearly seen here that person number 1 and person number 2 are phenotypically normal, but they have affected child, and this is male. Male is designated with square and female with a circle. So this is clearly seen that this is autosomal recessive genetic disorder that can skip generations and reappear later. So that give us genotype of parent 1 and 2. Both of them have to be heterozygous, so have to be capital A and small a, both of them. And of course this affected person, because this is recessive genetic disorder, have to be small a genotype. And when two parents who is both heterozygous, so parent 1 heterozygous and parent 2 also one heterozygous, the probability that they would have affected progeny would be, so here we would have phenotypically and genotypically normal progeny. Here we would have a carrier but phenotypically normal. Here also we would have a carrier but phenotypically normal. And here we would have homozygous recessive or affected child. And probability would be 1/4. So this is just for information. And as you see, this affected child marries unaffected person and all outcrossers, and here we have outcrosser here. That means that person is not directly related neither to person 1 or to person 2. So gene flows within a family, and those people whom I circle with green color would be all outcrossers, and we have to assume that these people have to be phenotypically and genotypically normal. So the genotype have to be capital A, because this is rare genetic disorder, so we have to consider all people outside the family to be phenotypically and genotypically normal. But here in our pedigree we have an exclusion. As you see, these two parents have affected progeny, and if parent number 1 in second generation, who is outcrosser, would be phenotypically and genotypically normal, we wouldn't see such results in their progeny. So here is an example. So female on the left, if her genotype would be capital A, and male's genotype would be small a, 100% of their progeny would be heterozygous, and that means that 100% of their progeny would be carriers but would be phenotypically normal, because this is homozygous recessive genetic disorder, and that give us information that female is not homozygous dominant. This give us information that this female have to be heterozygous. So in this scenario, if this female would be heterozygous, so capital A and small a genotype for her, that give us 50% of the progeny have to be homozygous recessive. That's why in the progeny we see that so many children are affected. So we can expect in the progeny that 50% would be affected, or 1/2. And this is exactly what we see here. Do not expect exactly 50% to be like 2 out of 4 to be affected, because numbers of progeny are small, and of course in such small sample we may have great deviations from the mean, from the predicted numbers, 50%. So now we can say for sure that genotype of the person number 5 is homozygous recessive, so small a, and we can say that genotype of the person number 2 here would be 100%. He is phenotypically normal, but he have to be carrier, so have to be heterozygous. We 100% sure, according to this Punnett square, that this person is heterozygous. And here we once again have exclusion from our rule. We have to assume before that this person is homozygous dominant, so normal. This is rare genetic disorder, and all outsiders from this family, all outcrossers, would be genotypically normal. But we have found that genotype of this person is heterozygous, and these two parents has affected child, and this is impossible, would be impossible if we would cross homozygous dominant and heterozygous. 50% of such cross would be homozygous dominant, and 50% of such a cross would be carriers or heterozygous, but we wouldn't be able to see none of the children who is going to be affected. That give us information that this female also carrier. So her phenotype is normal, but she is heterozygous, just like second parent. So what is the probability that person number 4 is carrier also? Because only 2 phenotypically normal people who is carriers can give progeny that who is going to be affected with this genetic disorder. Because if these 2 parents would be phenotypically and genotypically normal, there is no way how they would get affected progeny. Only if they would be phenotypically normal but would be carriers, there is a chance that they would have affected child. So probability that this person number 4 is a carrier would be 2 out of 3. So this person belongs to this category. So she is phenotypically normal. So we can exclude this variant, and the probability that she is heterozygous for this trait or carrier is 2 out of 3. So her probability to be heterozygous is 2 out of 3. And what is the probability of person number 5 in fourth generation to be also heterozygous or carrier? And let's take a look at his parents. His mother is homozygous recessive, and his father is homozygous dominant, we have to assume. And that gives us 100% probability that this person is a carrier. So if we build a Punnett square with one parent homozygous dominant, another parent homozygous recessive, as you understand, 100% of the progeny would be carriers. So this gives us probability 1 out of 1, or 100% this person is a carrier. So now we can calculate probability for them to have affected children or child. So female number 4, her probability to be a carrier is 2 out of 3, and the other parent has probability 1 out of 1. I may exclude this from my calculations, but I want to show you, because in other calculations you may need probability for the second parent also to be calculated. But in these calculations we can exclude, because anything we multiply by 1 would be the same number. But still I want to show you this in my calculation, so later in different calculations you would be not confused in this part. So, and also we have to calculate the probability if parent 1 would be heterozygous, parent 2 would be heterozygous. This is their probabilities, and if they both would be heterozygous, the probability that they would have affected child would be 1/4. So we have to multiply by 1/4. And as you see, probability that this couple here would have affected child would be 1/6. And this is going to be our answer today. And this is all for today. Thank you for your attention. Please subscribe for my new videos that I post almost every day. Thumbs up if you like this video. Please write your comments, questions if you have any, and see you in the next video. Goodbye.